three-dimensional shapes.
It's not. It's up.
But now we all realize what we're talking about is I had three objects or four objects that were equally spaced, one up, one here, one out from the board in this direction, out from the board, and one into the board, and all of them are the same distance from that spot. And then we realize it just doubles the amount of stuff, right?
Yeah.
In fact, it would be the same as if all of these objects were collected in one spot right there, except for the cosine part, right?
Yes.
Yeah.
Make sense? What if I put another object around this loop? I put another one here, another one here. Same thing would happen, right?
Yeah.
Another one here, another one here. So this would continue to go on, right? So you get the exact same thing except for the cosine piece, right?
Charge cosine non-charge.
Okay? So if I were to have, say, a ring, if I have a ring, and in the center of the ring going this way, remember the ring is coming out of the board, right? In and out of the board, right? It's flat, permeable of the board.
We understand.
Good.
Check
Wait, I'm
Just
pretty
checking.
sure that's an oval.
So that's because you're seeing it three-dimensional perspective. Good job.
Give me no.
I'm kidding.
All right, so
Walk around speed.
points right here. Good, we? Okay, so points right there. So if you're that distance out, I would try to figure out, so this is the cosine, right? That's my theta. If I'm calling this A and this R, I got to put the right letters on there. That would make this R. Wait, that's R. That's going to be X then.
X, yeah.
I'm about to say something's wrong here. And that's theta. Then each one of these would contribute, each little piece up here would contribute the same little bit, wouldn't it? It would be KQ over D squared. But I'm going to do the cosine theta because it's going to cancel out with a piece down here, right? So only cosines are going to matter, right? And what's interesting is each one of these little q's, if I add them up, they're just going to add up to one big Q, right?
Oh, yeah.
Are any of them any farther away?
No.
They're all the same. So this becomes KQ over R squared. Actually, it'd be little r because of the way I define that variable.
Hey, wow.
Cosine the angle between them.
Big Q is just the sum of all little Q's.
Yes, well, the total charge of the ring, right? Does that make sense? And if that's the case, then I can rewrite cosine in terms of the sides of this triangle, can't I? Specifically, R would really be the square root of a squared plus x squared. Going to pause there, make sure you catch that. So that would be my hypotenuse. And my adjacent side would be x, wouldn't it?
Yes.
So cosine can be rewritten. I can rewrite this expression here as KQ over R squared times x over square root of a squared plus x squared. Oh, I got an R squared over here too. Shouldn't I do that one too? I should get rid of that R squared. So that would also be a squared plus x squared square root squared, right? So the force, or the field felt at that point right there is going to be KQX over a squared plus x squared to the 3/2 power. Right, because there's a 1 power here, because these would cancel out, another half power here.
And you said the force at that.
Electric field at this point in space, away
Yeah.
from the ring, away from the center, has to be the center, specialized case, all the way through.
This is just something I'm going to memorize.
No, you have to drive it. They'll probably give it to you. Right? So the trick is to remember the trick. What's the trick?
Everything's
The cosine theta is the same for all of these. So you need to remember the piece. So you're going to start off with something like KQ over D squared. Then you're going to recognize that each one is the electric field, right? Or one piece. Then you're going to say something like E equals K. Now, if you want to be really technical, you want to wow the judge, you write DQ, right? Little bitty bit of charge, okay? Divided by the distance between them, R squared or something. Cosine theta. Cosine. And this is where the trick is. You have to pull this cosine theta out of thin air. Right? You have to remember, oh, it's the piece that's in this direction that matters, and that's what I'm summing up. So there's 4 cases. All of them are going to start here. All I'm going to have some sort of weird step that allows you to get to the finish line. Okay. On the previous one, it was the lambda dr gives you q.
So are these sorts of problems going to give you the number of particles around that ring?
No, they're going to say you have a charge per unit length or you have total charge on a ring of blah. And your job is to convert it to the form that we use it for. These are the assumption in all these cases is the charge is so ridiculously massive. There's so many charges that we couldn't possibly bother to keep track of them.
So if they gave you a charge per unit length,
I would turn it into a net charge in the ring,
so just multiply by
the circumference of the circle. And that happens often. That's something that they do. Okay?
Yep.
All right, 2 out of 4 shapes. How bad can it be?
Like, it's gonna get worse.
Yeah, the next one is by far the worst.
Oh my goodness.
Next one where I spend a lot of time waving my arms. Be good for Natalie to watch that. All right, here we go.
Oh, wow.
I've got a disc, and I'm a distance. What letter do they use? X still. X away from it. I'm going to the front of the next one.
This.
Got a disc.
Yeah. Like,
Now, how am I going to do this one? And why is it different from a ring?
Because you can have equal charge all over the face of the disc. So maybe
Right?
do a limit as a
But a disc, but charge up is going to be equal to charge down, right?
Yeah. You don't have to do multiple cosines for every angle in between.
Ah, the cosines are changing.
Hmm.
And the distance to that spot is changing. So since both of those are changing, we are going to be required to integrate, right? Because there's going to be the little bitty bit here is different than the little bitty bit just right next to it.
Yep.
Okay. So the approach we're going to use is creative. We're going to say, well, we already know how to deal with a ring, right? So instead of starting over from scratch, I'm going to use the ring formula we just invented and start with a small ring in the middle and integrate all the way out to the largest ring on the outside. Okay? I'm going to sum up all the electric fields caused by the littlest ring to the biggest ring. I have to integrate because ideally I'm looking for rings of infinitesimally skinny widths. Because as you pointed out, the effect of the inside of this ring is different than the effect of the outside of this ring. This is closer, this is farther. This has less charge, this has more charge. So it's too much to deal with. Fair enough? Okay, so we're going to want to integrate the rings. What's the ring formula? We just had it a second ago.
Hold on. KQ over R squared cosine theta equals electric field.
What was this one? Wait, sorry.
Uh,
K is KQ.
KQ over R squared
Okay.
cosine theta equals electric field.
Oh, except that we right ground it down to X's and A's. Can we do that
so
form of it?
K big Q X over
Okay,
A squared plus X squared to the 3/2.
And we're going to do the integral dr, right? As we make a radius bigger for our rings.
a little Q or a big Q.
Should be a big Q.
It was a big Q to begin with. We're going to play with that Q a lot
And
in a
that's
moment.
the collective charge.
That was a collective charge of one of the rings, right? And so now I'm going to rewrite that collective charge of one of the rings. So what are we talking about when we talk about this? We're no longer talking about our charge per unit length. What are we talking about?
Per unit area.
Charge per unit area. So I can write Q. I can write Q as my charge per unit area times my little bitty bit of area. So far, so good? Now, that's going to get tricky, so I got to figure out how I'm going to write area of this. What is the area of that thing?
Which circles matter.
What is it? What is the area of a ring?
Big circle
Minus
minus small circle.
Big circle minus small circle. I'm going to change that just a smidge. Okay, I'm going to argue with you just a smidge. I'm going to say, what if I were to cut this? Pull it out like a big piece of Play-Doh snake,
Linear algebra.
right? If I were to cut this little ring and I were to pull it out like a snake, it would look like this, wouldn't it? More or less.
A little bit.
And then this piece here would be the circumference, which is 2 pi r. And this little piece would be the change in r's, which would be dangerous because if the r's would be different, wouldn't they? Which would change my answer because it really looked like this. But the smaller I make the r in this direction, the change in r, the closer it approaches 0 difference between the two. So if I were to, say, integrate this with respect to r, that would be my area piece of a ring.
Just dr.
dr. So it would be 2 pi r with circumference times whatever this little bitty piece here is, which I'm going to shrink to 0 so I don't have this strange angle piece, right? So if I go to set that up, that's my area.
Wait, when your height approached 0 too, and therefore you'd have 0 be approaching 0.
That's what I'm with 0. And no, this would, well, this is how far I'm going this way. So this is a different r, if you think about it. We're talking about this dimension here when I'm trying to make these smaller and smaller. Whereas this r is actually just how far you are from the center. Okay, that wouldn't change. Okay? So as I start to place this up, I go, okay, so that's my area. So, but that's not my charge. So how am I going to fix this problem? That's not my charge. So how do I fix this problem? I have to use this piece over here. I'm going to say, well, my hat boy times my area, which is now going to be 2 pi r dr, right? Because I'm going to have to integrate that. That's my q, right? That's this thing right here. And I put a dr in there way too early. That's my bad. Let's just leave that integral off temporarily. Realize better. So if that's the case, then the rest of this stuff is k. Now I got to think really hard. X isn't going to change at all. What was a?
That was our y side of the triangle.
That was our r, wasn't it?
Yeah.
So this is actually also going to be in here to the 3/2. Integral dr. There's only one person in this room that can do this problem.
Oh,
One of them's at home.
wait, Mr.
The other one's at home. Let me pause this. Oh, wait, there's 2 people